Hello, AP Chemistry. Today we are going to talk about the relationship between the E naught of the cell that you learned about yesterday for voltaic cells and the spontaneity of redox reactions. Now, before we get into the spontaneity and relating this to delta G, we need to talk a little bit about what it means to have electrical potential energy. We're going to relate that to gravitational potential energy by going back to our physics and remembering that in physics, gravitational potential energy, GPE, is calculated by the mass times the gravitational field times the height. Now, in terms of units, the gravitational potential energy, or any potential energy, is listed in joules. Mass is kilograms. Gravitational field is in newtons per kilogram, and the height is in meters. So these are the units that we're going to get into gravitational potential energy. And if we group the last two of these, so that we're going to group the gravitational field and the height, this is going to give us a gravitational potential. And the gravitational potential, if we also group our two units of newtons and meters, is going to give us that the joules in the gravitational potential energy is equal to the kilograms. Oh, I changed color on you. Times Newton times meter is just a joule. So we've got joules there divided by kilograms. And this is giving us the gravitational potential, which is illustrated in the diagram up to the right. So just like gravitational potential does not depend on the mass, we're going to see that the electrical potential doesn't depend on the charge, but multiplying the two is going to get us the potential energy. So the gravitational potential only depends on the height from the ground for each of these rocks. But on the left, we see a rock that has a mass of 1 kilogram at a height of 2 meters. It has a gravitational potential of negative 20 joules. If we double the mass to 2 kilograms, we're going to double the potential energy, and that's going to be 40 joules. So even though they have the same gravitational potential at the same height, that they have different gravitational potential energies. This is kind of analogous to a waterfall, in which the height of the waterfall times the gravitational potential is going to give us the gravitational potential, but then the amount of water coming over is going to give us the energy that we're going to get out of it. So likewise, for a voltage, down below we have a diagram showing a charge on a sphere, and then two charges off to the right of that sphere. And electrical potential energy, again, is going to be in units of joules. But now to get the electrical potential energy, remember that the electrical potential energy is equal to, so that's equal to Q times E, where Q is the charge. So that equals the charge, which is in units of coulombs, and the electrical potential, the E, is actually in joules per coulomb. And if you remember joules per coulomb, that's actually units of volts. So a joule per coulomb is equal to 1 volt. And rearranging that 1 joule is equal to 1 volt times a coulomb. And so these are going to help us to understand as we move further along. And just to illustrate to the right, suppose that at this distance we have an electrical potential of 10 volts. Let me write that V, 10 volts or 10 joules per coulomb. Then anything with a unit of 1 coulomb is going to have, so 1 coulomb is going to have a 10 joule potential energy. Something that has 2 coulombs is going to have 20 joule potential energy. So this is very analogous to the rocks up above. So this Q times E, or the potential energy, can be rewritten if we take that Q and realize that Q is actually going to be the number of electrons that we have. And the number of electrons is going to give us a charge based on what we call Faraday's constant, where the N times the F is Faraday's constant times the charge times the number of moles of electrons. And this is the charge in coulombs on the electrons that are being used and are being pushed through the electrochemical, the outer wire from the electrochemical cell. So the electrical potential energy is just going to be NF times the E of the cell, where the E of the cell is the joules per coulomb. And notice everything cancels out now except for the joules, and that leaves us with our potential energy. Now, let's bring that together with our delta G. At first, we're going to look at delta G not as the delta G naught, not standard state, but we're going to get to standard state in a few moments. That the delta G of whatever reaction we're looking at is the driving force. That's the free energy of the reaction. And so the potential energy of that system, of that reaction, is essentially the work that's being done by the electrons as they go through the external circuit to light your lights or to power your devices. So this is negative W. This is the work. So the maximum work that can be done by a particular system is that delta G, and that then equals the negative electrical potential energy, which is negative NFE of the cell. So we have our first equation coming from this relationship, and this NFE of the cell is related to, you'll see in a moment, the equation that you see on your reference charts relating the delta G and the E of the cell. Looking at this equation, you can see that if the E of the cell is positive, a positive voltage, a spontaneous reaction, or thermodynamically favorable, then the reaction is spontaneous. I should have looked ahead. And the movement of electrons in the circuit will do work. This is the spontaneous electrochemical cell, the voltaic cells that you saw in class yesterday, and that we'll be seeing in our lab later on this week. So the relationship between the delta G and the E of the cell is that a negative delta G gives us a positive E cell, or the other way around. And that's going to get us work being done in the cell. At equilibrium, everything is there's no net reaction. So the delta G is 0 and the E of the cell is 0. And in a non-spontaneous cell, this would be an electrolytic cell. This would be a cell that we're going to see next week, in which it requires the input of work. It requires the input of energy, and that would be a positive delta G, or a negative cell potential. So suppose we have this equation, this reaction, in which zinc is going to be oxidized from 0 to 2 plus. And to do so, that zinc is going to lose 2 electrons. The copper 2 plus is going to be reduced to copper metal, and that to do so, that's going to gain 2 electrons. And so this shows us the first thing that we always have to do when calculating the delta G of the reaction. So this particular cell, it's not at standard state necessarily, has a voltage of 0.900 volts. So it's spontaneous, and so that should give us a negative delta G. Notice that in the delta G equation, we have the number of electrons that are being transferred in the reaction. And so this is telling us that the N for this reaction is 2 We're going to say moles of electrons because we're going to assume that there's 1 mole of the reaction occurring. All right, so there's 2 moles of electrons transferred, and that's going to go into our delta G equation. So plugging everything in, the delta G now is equal to negative times 2 moles of electrons. Faraday's constant, 96,485 coulombs per mole of electrons. They used to use just 96,500 coulombs per mole of electrons for Faraday's constant, and occasionally you'll see us still using that in our answer keys. I don't know why they went to this more precise value, but since that's what's on your reference chart, go ahead and use it. Multiply that by the 0.900 volts. Notice also this is going to be seeing why we don't multiply the voltage by the number of electrons, because it's not until we get to delta G that we need to worry about the number of electrons. The voltage is per electron. And when we do this calculation, we get negative 173,673 joules, or negative 174 kilojoules. Notice the joules came out of the coulombs times the volt. Remember up above we said that a coulomb times a volt is equal to a joule. So that unit popped out of there, and the moles of the electrons canceled out. So now let's take a look at what happens at standard state conditions and come up with a couple of equations that are going to be useful for us. And we're also going to relate the delta G and the E naught for the cell to K by the triangle that you see at the lower right. So standard conditions, again, 1 molar concentration and 1 atmosphere pressure. We're also going to see that there's going to be a time when we're going to standardize. It's not standard conditions, but standardize on 25 degrees C to help you guys out with some of those calculations. So just putting the standard conditions on, we're going to put the naught in there, and we come up with the first equation that's on your reference chart. Is that the delta E is equal to negative NF E naught, delta G naught, sorry, is negative NF E naught for the cell. Now, we remember there's actually another equation on your reference chart, that the delta G naught is equal to negative RT times the natural log of K. And so if we set those two equal to each other, we find that negative NF times the E naught, what's going on there? Sorry about that, times the E naught for the cell is equal to negative RT times the natural log of K. And we can rearrange that to show that the E naught for a cell is equal to RT divided by NF times the natural log of K. Now, this equation you can see over here on the right. So we've drawn both of those equations into one equation to calculate the E naught for the cell directly from the equilibrium constant, or vice versa. In your book, they make a simplification here, which is really useful. If we say we're at 25 degrees Celsius, or 298 Kelvin, and we recognize that keeping that temperature constant, that R is a constant and F is a constant. So if we standardize on T as a constant, we've got 3 constants in here. And so what we're going to do is rewrite this using those constants. And we're going to say that the E naught for the cell is equal to R is 8.31 joules divided by mole times Kelvin, the temperature 298 Kelvin, divided by N is the only thing that's going to be variable because that depends on the reaction, and Faraday's constant at 96,485 coulombs per mole of electrons, and multiply it all by the natural log of K. And when you do this, you get a nice simplification that the book gives you. It's not on your reference chart, but you can make use of this anytime you need to. And if we have a test on this, we will give you this equation that the E naught for the cell is equal to 0.0257. Now, we are going to have the unit volt in there. Let's see, how does that fall out? We've got joules here divided by coulomb. A joule per coulomb is a volt. The K's cancel and the moles cancel. So we got volts divided by the number of electrons transferred times the natural log of K. And this is a very useful equation to help simplify. If you want to put in the RT and F and see for yourself that it works, go ahead and do that. And remember, this is always going to be at 25 degrees Celsius. All right, so go ahead and commit that equation to memory. So let's put that equation to use in a practical practice question. And we're going to look at a reaction in which we have silver being oxidized from silver to silver plus, and the oxygen is going to be reduced from oxygen 0 to it's a -2 in the water. And so the oxidation reaction has silver being oxidized to silver plus, and we need 1 electron for that. And the cell potential for this, if you look this up on the reference, on the standard reduction potentials, is 0.80 volts. The reduction reaction is O2. Now, we need a couple of more things in here. As in 19.1, you could balance this, but I'm going to go ahead and do it for you. The O2, we need to have 4 H pluses first, and then 4 electrons, and that all combines to form 2 water molecules. And the potential for that is 1.23 volts. These are both positive. Let me put positive signs in front of them. And then to combine everything, we'll notice that we have 4 electrons being transferred here. So we need to multiply the first reaction by 4. Remember, don't multiply the voltage by 4. That will be taken care of in the NFE part, the 4 electrons. But we do need to either multiply this by -1 or subtract it, because this is the reverse reaction. Don't do both. Either multiply it by -1 or subtract. Don't do both. And so we get the overall reaction is 4 silver plus O2 plus 4 H plus is going to make 4 silver plus 2 H2O. And then the E naught for this cell, 1.23 volts minus 0.80 volts, or 0.43 volts, is the E naught for this cell. So now we can calculate both the standard free energy, because we have the overall reaction and the overall E cell, and the equilibrium constant. Let's do the free energy first. So the standard free energy, delta G naught, for this reaction is -NF times the E naught for the cell, -4 moles of electrons times F, 96,485 coulombs, that should be a C, per mole of electrons, and 0.43 volts. And I won't cancel out units for you. You can do that for yourself. That equals -1.66 times 10 to the 5th joules. A very spontaneous reaction. Notice this has a huge negative delta G, 166 kilojoules. And compare that to the E cell. It's a relatively small cell voltage, gives us very large delta G naught. So the relationship between delta G naught and E naught is simple to use. To calculate the equilibrium constant, we're now going to use the delta G naught that we just calculated and go back to that other equation from chapter 18, that the delta G naught is equal to negative RT times the natural log of K. So I'm sorry, I said that should be a negative sign up there, negative 166. So rearranging, we get that the natural log of K is equal to delta G naught, take the negative, over R times T. And plugging in our numbers, we have negative 1.66 times 10 to the fifth joules. You've got to keep this in joules because R is in joules. R is 8.31 times 10, 8.31 joules per mole times Kelvin. And let's go ahead, we can throw a joules per mole in there as well. It's moles of reaction. Otherwise, we're going to have an extra mole hanging around here. And we're going to say this is at 298 Kelvin. Did we say that up above? That it was supposed to be at 298 or 25 degrees C. We didn't, but unless we say otherwise, then let's assume that we're always going to be at 298 K. So 298 K. And that gives us 67.03. And since that's the natural log of K, K then is equal to E to the 67.03. It's going to be a pretty big number, 1.28 times 10 to the 29th. And I would say that is a K that definitely favors your products. Now, the last thing we're going to do, and then we'll be done, is we could directly convert from E naught of the cell to K by using that last leg of the triangle, that last equation that I gave you, that the E naught for the cell is equal to, and let's just go ahead and use 0.0257 volts over N times the natural log of K, and plug everything in. We've got 0.43 volts is equal to 0.0257 volts, so the volts are going to cancel. Remember, we had those 4 electrons in there times the natural log of K. So rearranging everything, the natural log of K is equal to 0.43 volts times those 4 electrons divided by 0.0257 volts. So there's where the volts cancel out. And that equals 66.93. And so the K is equal to 1.16 times 10 to the 29th. And we probably have a few too many sig figs in there because that's really, really close to what we saw before. And that's going to be close enough for us to say that they're equal. There's some rounding that goes on in there. And when you put exponents in there, it's really going to become compounded. But both of those, the log Ks, you can probably round them both to 67 to get the same number. Okay, so we have seen the relationship between the E naught for the cell and spontaneity, both in terms of the delta G naught and the K. Remember that whenever you have one being spontaneous, the other two have to show up as being spontaneous as well. Likewise, if one is not spontaneous, or if one is at equilibrium, the other two have to follow suit. So watch out for those.